Okay, good, yeah. So I'm going to tell you about this little AI side project I've been working on. But before we get started, Masashi, I just need your help with something.
Sure.
I got this application, and it's by this guy Haruto Nakamura, and I just want you to look very briefly at this slide and tell me whether we should accept him or not. Is it a strong application or not that strong? Let's see, he's got experience in neutrino oscillations. It's very nice. He's from the Tokyo Institute of Technology. He's good at Python, MATLAB. I don't know about that, but C++.
My mother tongue.
He's got a whole Yay or nay?
It's really, I need some more time.
Need some more time? Undecided? Okay, well, this is of course not a real this is not a real person. I just wrote, I asked ChatGPT, the International Center for Quantum Field Measurement Systems for Studies of the Universe and Particles, QUP, runs an internship program. Give me an example of a strong application. So I thought it was pretty good. I probably would have said yes. I don't know. So AI has become a real popular topic lately. 2016, Google DeepMind came up with a Go playing program. So chess, 1997, Garry Kasparov was the world champion. He was beaten by a computer. But, chess has a relatively modest branching ratio, meaning at any state in the game, you only have so many options. And algorithms had gotten pretty good back then. And if you asked the experts in the field, surveys were done, like how long do you think it'll be before a Go playing program will beat a computer? Most of the estimates were in the 2030s, 2040s, 2050s, right? But in 2016, they did it. So they used some of these newfangled machine learning algorithms, actually using self-play, and beat the world champion. And in what fashion too? So in 2019, he announced his retirement from professional play, stating, even if I become the #1, there is an entity that cannot be defeated. So, and it did it in quite the style too. There's this famous move 37 that Go players across the world really find a very beautiful and creative move in a way that is very clever that a human never would have thought of, right? Here's another example of popularity in AI. Have you ever seen this one? The Pope in this little drip puffer coat, It looks pretty good, but yeah, I thought that was real, but it's not. Yeah, Donald Trump and some weird with big muscles, and I don't think that's real either. This guy I saw in the news, actually, this person got quite popular, I think, motorcycling around Japan, and turns out it's not a girl at all. It's this dude on the right, just using a really good filter, and people didn't know. This influencer is selling, I don't know, beauty products or something on Instagram and making quite the money, $11,000 a month. But she doesn't exist. It's completely AI art, completely made up. It's a beautiful picture. I mean, you can look at it 4K and it looks like a person, but it's completely AI generated. But let's not get too excited about AI at the same time, or let's at least exercise a measure of caution. If we look at the historical track record, so you read a book about AI, there were these two periods where somehow AI was invented and then the hype got away from the actual scientific progress, right? From the technical progress in the field. And that's when you have an over-promising and an under-delivering, which stops the field from really being interested in working on it for a while, so-called AI winter. And this happened twice. And the question is, right now, AI is very popular. We're probably at a level of over-promising and under-delivering, maybe, maybe not. Who knows? Will it happen again? Will we have another AI winter where nobody cares about AI? Most AI researchers these days would say, no, AI is here to stay. We're not going to have another AI winter, but we don't know, right? And so what I wrote here is it's important to have a nuanced and precise understanding of AI's capabilities and limitations. Right, so let's exercise a measure of sort of a scientific attitude towards it. So what is AI? So here are my definitions. You'll hear a lot of definitions for AI, machine learning, deep learning, et cetera. Here are my definitions. So I think AI is doing something with a computer that a human could only do with intelligence, right? So it's intelligence with a computer And then, so I'm sort of pushing the ball forward a little bit. I'm saying maybe you have to define intelligence now in order to define AI. But anyway, it's the computer equivalent of what would take intelligence for a human. And for machine learning, it's an algorithm that learns from data, but without being programmed how to do so. So if I have some data points and I say, okay, this is probably a good straight line, I can extrapolate from this or whatever. I'm saying, okay, now minimize the least square differences between your data points and the line, and that'll give me the coefficients that describe this line. That's an explicit algorithm, right? I've told it exactly how I want the algorithm to go fit that data. But machine learning algorithms are algorithms that are more implicit. You give it a bunch of data and it somehow learns, and you don't keep control of how or exactly in what way. And then deep learning is the subset of machine learning that uses artificial neural networks, which is the subject of the remainder of the talk. And these tools, these AI tools, they supplement traditional statistical tools. Traditional statistical tools are great, especially for independent and identically distributed variables, IID. But beyond the IID assumption, it can be infeasible to compute certain quantities. So for example, for my PhD thesis, I think I wrote in my thesis a little footnote that said I spent 180,000 CPU hours on this calculation, and I was not using machine learning tools. And when I think about that, that's not just like a lot of resources and a lot of money, but like that also came out of the power grid and probably put a metric ton of CO2 into the atmosphere, right? So there's a real cost to large computations, and machine learning can help with that. And so here's the Venn diagram. And so traditionally, I've lived in this space, and I'm really interested in diving into that direction of the Venn diagram. So let me just go back to basics briefly here and say, how does an artificial neural network actually work? So the original artificial neural network looks like this. It's called the perceptron algorithm. It's very old. And it works like this. So you take a bunch of inputs, they're called features, and then you have a bunch of pre-computed weights, which multiply these input numbers. You then sum all these weights together, add a bias, hit it with a nonlinear activation function of some kind, and then you have your output. And by feeding it a bunch of data and by in a supervised way training this thing, so you have a bunch of data where you know what the answer should be, you can have some kind of loss function, some kind of thing of how close the answer that you got is to the answer that you know is correct. And you can figure out what this bias in these weights should be. So that's the backwards pass of learning these parameters, and that's how you train a model. And the forward pass is giving you predictions given a bunch of inputs. So this is a single neuron here. So you got a weights, a bias, and a nonlinear activation function. It's called the perceptron algorithm. And then what people figured out, so here's an example of the perceptron algorithm working. I've got here two features, one's domestication and the other one is size. And so at first the neural network is somewhat randomly initialized, and then as I feed it more data, I can train it to try to find some optimal boundary between a predictor of is it a cat or is it a dog based on how domesticated and what size the animal is. And so as you give it more data, it becomes better at it, right? And you can improve, so that's how that works. Then you've got this idea of a multi-layer perceptron algorithm. The idea here is that instead of taking a bunch of inputs, putting it into a neuron that has an output, you have a bunch of layers of neurons, and the inputs for these neurons are the outputs of the previous layer. So this is the multi-layer perceptron algorithm. Note that if you have a linear activation function, so if you basically don't have an activation function, this comes down to a matrix multiplication. And so you have a matrix of weights, a matrix of weights, and a matrix of weights. These all get multiplied, and you end up with just one matrix worth of free parameters. So the nonlinearity is really key to this thing working, right? If you don't have a nonlinearity, it's just one layer. It comes down to just being one layer. And beyond NLP, multi-layer perceptron, there are many other deep learning architectures, a bunch of really cool ideas. For example, residual neural networks that allow a bunch of skip connections, recurrent neural networks where it's not strictly feed forward, convolutional neural networks. Louis works with these a lot. These are great for image processing, GANs and transformers. And the sort of what I think are probably three of the big milestones in the current deep learning revolution are that in 2012, so for years, Google was holding this competition called ImageNet, and you had a bunch of images and you had to perform some tasks on them. And for years, there wasn't that much progress until this one solution called AlexNet came along, which for the first time used deep learning, people used a deep neural net, and just blew the competition away, right? It was much better than all the other algorithms. And I think that's really what sparked the modern deep learning revolution. And that's not very long ago, right? 2012. And out of all these architectures, the transformer has really taken the world by storm. The transformer was invented in 2019, a bunch of Google authors and one guy from the University of Toronto. And this architecture seems to be very efficient in many different fields, actually. Originally, it was just for translation, but it's found its place in many non-translation language tasks, and also in computer vision, actually. Transformers are getting increasingly popular. We'll see if that sticks. And so the transformer, I mean, it's kind of similar to the multi-layer perceptron, but instead of these static weights that you update, it has a kind of dynamic weight using keys and queries and values, where the layer looks at the last layer's output and is looking for a certain pattern in that output using a query that has to match a key and that it has some value that it sends forward to the next layer. So machine learning, I would say, currently is a bit of an art, bit of a science. It takes a certain je ne sais quoi, a certain finesse to be really good at machine learning. I mean, part of the problem is that neural networks are these giant weight matrices, right? And it's like, what's it doing? How's it getting to the output? And it's kind of hard to inspect, although there are some ways, things like mechanistic interpretability, where people are really trying to figure out what's happening inside the network. And currently, I would say in my reading of the field, right, I'm fairly new to this, is that it's full of intuition and following best practices. And here's an example of a scaling law. So these guys were training a large language model, and they were getting some quality, some loss function, right? So you want this to be as low as possible. And then depending on how much compute they spent on the project, they got better and better loss functions. You know, you just compute for longer, you get your algorithm gets smarter or something, or your neural network gets smarter. And then they found that if you train a small network for a long time, the parameters are very good, but you don't have very many of them. And if you have too many parameters and you don't train them enough, then they're full of noise and not that useful. And this is kind of optimum. That's a function of how much compute there is. So you can draw this locus through here. That's a prescription for if I have this much compute available, how big should I make my large language model? And these kinds of things are all over machine learning, where there's an empirical way, best way of doing things, right? That's not derived from first principles, but that's it's empirical, it's observation. This was on Twitter earlier this week. There was someone giving a course at Cornell called Intelligent Systems. And on his front slide, he had changing random stuff until your programs works is hacky and bad coding practice. But if you do it fast enough, it's machine learning and pays 4 times your current salary. Yeah, I don't know. But the top comment under that post was stochastic gradient descent is a better programmer than you are. So if you just keep trying things and you have a metric to see if it worked or not, you might end up with a better solution that your mind ever was able to come up with, right? Here's a little side on AI art, kind of where the basis behind it. This is called a diffusion model. It's actually a misnomer. There's nothing diffusion about it. You know, if I imagine I have some image with a delta function in it, then diffusion, you know, would spread that out. That's not at all what's happening here. Instead, what you do is you have some input image that you like, that's high quality, high resolution, or showing the kind of object that you like. And then what you do is you add a little bit of Gaussian random noise to it. So this is what they wrongly call diffusion, because they don't know physics, I guess. And then what they do is they have a neural network try to denoise it and get back to the original image. So how close it gets to the original image is the loss function. So at first it's randomly initialized and it just makes it all worse, right? So the loss function is terrible. And then as you continue to feed it more examples, more images, it starts getting really good and it's able to sort of, from a noisy image, figure out what the underlying denoised image is. So that's how the diffusion model works. And you know, the thing that's I think really interesting here is this flow of like the forward and the backward thing, right? You start with data where you kind of know the answer, and then you make it a little bit worse, and you try to get the network to reconstruct what you originally had there, and that's how the training works. AI is finding lots of uses in cosmology too. This is a really cool paper from quite some time ago already. So there are these things in optical images of galaxies called strong lenses, where the light from a background galaxy can be significantly amplified and distorted by matter that's intervening. So for example, here, this galaxy, which has some large dark matter halo around it, actually lensed a background galaxy into an image here and an image there and some other image somewhere else. And I'm not so good at these, as you can tell, but there are these astronomers that have really good biological neural nets in their heads that can really figure out from an image like this, like, oh, that galaxy is over here, and that one got lensed. Look, this one's a tiny image of that one. They got, you know, and they really can figure out the physics of what's happening because they've looked at so many of these, right? And so we can do this with an artificial neural network, and those artificial neural networks are now, I think now I'm not sure if they're better than like the best astronomer, but they're definitely better than like the 99th percentile of astronomers or something, right? At reconstructing what happened here with the lens. And actually whether there's a strong lensing arc at all. The nice thing too is that the selection function is very well understood, because a human looking at these images might, you know, have just come from the bar and now they're not as good at it or something, you know, whereas the algorithm will always give you the same answer, because you can really characterize how good it is on simulations and you know it performs the same, as long as your simulations are relatively faithful. Another way AI can help us is I started this little project, this is from a while ago, where I used to read papers all the time. I used to read the astroph.co, so all the cosmology papers for the day, every day during grad school, and that was pretty onerous, you know, there was a lot of work. You know, no offense to us, but sometimes papers aren't that interesting to me. And sometimes they are, you know, and then I hear about it later, I'm like, damn, I missed that, you know, how did I miss that? So I started this little tool. I got a lot of this is copied from a computer scientist, and I made it publicly available. So any cosmologists in the audience, you know, or if you like instrumentation, astronomical instrumentation, you're welcome to go to this IP address and use it. You just put a username in and you start tagging some papers. As you can see, I tagged maybe like 100 papers. And I just tried this on Monday or whatever, and it said, oh, you should read, the top recommendation I have for you is you should read this paper. And actually, CMB lensing reconstructing biases from masking extragalactic sources. I haven't read it yet, but I really want to now that I'm looking at that, right? So it's a really good recommendation for me. And it's pretty simple. It's just using a support vector machine over these TF-IDF features. And it's recommending good stuff. Okay, Groundberg paper. Here, this was Ipei was our colloquium speaker a few colloquia ago. So it's very relevant stuff. Another way AI can help us. So now let's get to large language models. The training process goes like this. So in the same way that I had an image that I make noisier and then I try to reconstruct the original, the large language model is trained on next word prediction. So first I split my data into a training set and an evaluation set, and then I start training on the training set. So let's say my training set contains this sentence here: large language models are transformer-based, blah, blah, blah. So then I would start with nothing at all, and then I would say, what's the probability of the word large? Then I would start with large and say, what's the probability of the word language? And at each stage, let's say we're at this stage here, we put these first 4 words, and then we feed those into the network, all of the other neurons are left blank. And then the network puts out some probabilities at the end of it, where it assigns a certain probability to each of those, and then we tell it, you know, the correct word was transformer, which you gave 6%. So we now know the loss function, and then we can backpropagate this, so we can figure out the partial derivatives with respect to this answer all the way back through the network to find out how to take a step in the right direction, right? How to take all of these, the super high dimensional space of all of the neural network parameters, and take a step towards giving it assigning transformer a higher probability next time. And
can I ask a quick question? Do you have a fixed number of output nodes, or what's?
Yeah. So you have something like 32,000 words, and these are actually word chunks called tokens, and those are your outputs, and you assign probabilities to each of them.
Okay.
And like some of them are like a whole word, but some of them are just like an ASCII character or something, you know, so you can end up making any text out of that library of tokens.
Okay.
So this is how the training works. And if you look, for example, this is a real training run I did on cosmosage, where I measured the loss. So at first, the model learns extremely quickly from a small amount of text. This is probably capturing some kind of, it's hard to say, but probably capturing some kind of style or how much white space I use or like things like that. And then the loss continues to gradually improve. And then what happens is I run out of data, right? So this is all the training data I have. Like, I wish I could keep going, but I don't have any more data. And so let's just feed the same data back in, let's re-randomize the order of it all, and let's go over my data set again. And all of a sudden, the loss is much better. So what happened is that the model memorized a little bit of the language, and that's not what I'm trying to get it to do. I'm trying to give it some generalizing power, so it really understands the text a little bit. But that's what the validation set, the evaluation set is for. So the evaluation set is a set that I've kept aside. I'm only measuring the loss on, I'm not training on it. And it's shown here in this dotted line. You see it keeps going down for a while. So that's good, it means the model is still getting better at generalizing, even though it's memorized a little bit of the text. And then on the third time, I'm out of data again, let's do for a third time the data. So I started training again. It's much better again. So it's memorized even better, my training set. And now you can see the derivative flips over. So the ability to generate text that it hasn't been trained on gets worse, this overfitting. And that's when I said, okay, let's stop. This is my training run. I've gotten all I can out of this data. Does that make sense? Yeah. So here's a little bit on the landscape of large language models right now. I'm relatively up to date on this stuff, so feel free to ask for more details, but basically, there's the commercial side of things. So you've got OpenAI, Anthropic, Google, and some others. And then there's the open source side of things. So Facebook or Meta actually open sourced one of their large pre-trained models, and a lot of that really started this explosion, this proliferation of open source models that are fine-tuned on different things. And the point of this talk is to show you one more of these open source models that I've trained specifically on cosmology data. And the commercial models are the best. So currently the best model is OpenAI's GPT-4. And the nice thing is that the open source models are not too far behind. So I really like this as a benchmark. This is a cool site that you can go to called the Chatbot Arena. So you go on here instead of going to ChatGPT, right? And you type in your prompt, you use your large language model as you normally would. And instead of one answer, you get two answers side by side that get generated. And they're from two different language models, and you don't know which, right? They've just been labeled A and B. And so then what you get to do is you say, I like A better or I like B better. And in this way, they play the models against each other with random humans voting. And they do some bootstrapping to get the error bars, and this is how good the models are, right? And so this is an ELO rating, standard ELO, just like in chess or in whatever, Go. And so a delta ELO of 100, which is two of these tick marks, is a 64% win rate. And so the nearest open source model, which is this Mixtral 8x7B, isn't, not that far. It might be 70, might win 30% of the time against the strongest model. So it's not that much worse than the strongest model, GPT-4. And I just have one more note saying, this is a rapidly evolving space, and who knows, this might be valid today, but might not be valid tomorrow. Maybe OpenAI drops GPT-5 and the commercial is really far ahead, or maybe Mistral or somebody else figures out how to make a really strong open source model that beats out GPT-4. Actually, I saw that Meta is training Llama 3 and open sourcing it, so it may be that the strongest model next, it could be fully open source. It could be really cool. For cosmosage, I picked a relatively small model. I picked Mistral 7B, which it's not on here. So here's the idea, right? Here's the idea behind cosmosage. So why would I even bother? I don't have 100,000 GPUs. I can't do what these big companies do. Why would I try to make a cosmology assistant? Well, here's the hope, right? So the hope is that a very large model is very powerful, but it has to do all kinds of things. It has to give people therapy and be a friend to them and answer questions about finance and whatever. But if you can narrow the scope enough, if you can have a focused enough model, then even though it's of modest size, it may be more powerful than a very large generalist model. And this is generally thought to be true, at least it's true that in the limit, if your model is sufficiently, if the scope is sufficiently narrow, your model will be very powerful. So what did I do? I think the most important ingredient here is the data. It's, as they say, garbage in, garbage out. So if your data is very good, your model can be very good. If your data is not very good, your model will never be very good. So like I said, I started with Mistral 7B, which has 7 billion parameters. So that's about, at 16 bits per parameter, that would be 14 gigabytes of just weight matrices, right? It's at float 16. And then I needed the following. I needed GPUs, so I'm using the computer under Louis' desk. And usually this is limited by either the total amount of memory, like actually I'll just say it is limited by the total amount of GPU memory. So our GPU has 48 gigabytes, and I wish that number was larger. Software, I'm obviously using many Python libraries and stuff, but I wrote the top end stuff myself. And then data, there's 3 things that are important: quantity, quality, and variety. Quantity, you need a lot. You need a lot of data. Quality, garbage in, garbage out. And variety, actually, if your data set is too focused, it stops being able to generalize. And so this is roughly the data set that I trained the 4th version of cosmosage on. I have a larger data set I'm working on for the 5th version. So I start with a 2-step process. The first step is called fine tuning, which is just this continued pre-training. It's just next token prediction. What is the next word in the sequence? And this is a good way to sort of imbue the model with new knowledge. And so I'm training on a bunch of physics textbooks I found on the internet, a bunch of astro textbooks I found on the internet, a whole bunch of papers from the archive, and the Wikipedia part of cosmology, although I did have to heavily filter that, because if you just search for cosmology, you get a lot of pages on like Norse cosmology and the indigenous peoples of, some, so cosmology apparently means more than the scientific discipline. And then, I was kind of an idiot when I started this. I was like, damn, I need some really high quality data. So I just started typing. I was like, how does the CMB, why are there hot spots and cold spots in the CMB? And then I started like typing the answer, and I spent like a whole afternoon doing this. And I was like, oh man, I've made like 1 kilobyte worth of data, and I need to get to like a gigabyte, so that was completely hopeless. So you'll see here the data I was able to produce by searching the internet and typing some stuff myself. It's too thin. It doesn't even show up on the pie charts, right? So there's no way you can make a dent on data with one person, probably in a lifetime. I'm not sure about that, but it would take a long time anyway. So here's the data sets I used. I used a publicly available data set for sort of math and coding and logical reasoning. The big data set that asks the model to do various things, and then it has to follow instructions. It's supervised, right? So that you ask it to do something, and then it does it very well in the example, and that's what you train on. And then actually the biggest chunk here is the synthetic QA data, where I first let a strong language model read the paper and then ask a question to itself and then answer it nicely after just having the paper still in its context. And so in that way, I was able to make synthetic question answer pairs, and those are very high quality because they're produced by language models. They have perfect grammar, all the white space is correct, and all that sort of thing, right? So it's a very high. If I just try to take in this case, these papers were just generated from the LaTeX file or from the PDF, and they're kind of full of junk. They have like the LaTeX escape commands and like all kinds of junk. But when you do it synthetically like this, you get really nice, just all, good English and stuff. Okay. How am I doing on time? I feel like I'm taking a long, okay. So last time I gave the short version of this talk, Chris asked me a question, actually. He said, how did you pick all these archive papers, because there are some great ones and some not so great ones out there. So here's a slide giving an answer. Sorry for the belated answer, but here you go. So I use that same thing I showed before, where that recommendation service that I host, a bunch of members in the CMB community, like I've shown this around to like all the collaborations that I'm a member of, and a bunch of the CMB people I know. And some of them have taken to using this. And so I can go into the database because I host this and just see what are all the, anonymously, what are all the upvoted papers that people liked. And doing that, and also some other things, like I search for certain keywords and whatever, I get about 1,000 papers that I think are pretty good. And then I ask this service, I say, given those 1,000 papers, what other papers would you recommend, right? And that's how I extend the list to about 8,000 papers. And so that's my training set. One slide on prompt engineering. This is kind of getting to be a bit of a meme word, but what it means is it's sort of the art of asking the question in the right manner. So very famously, what's the famous example? Tom Cruise. So they say, if you ask ChatGPT, who's Tom Cruise's mother? It knows. So it gives you, oh, it's Mary Lee Pfeiffer. She was born in blah, blah, blah. And it like knows all this stuff, right? Because it's read Wikipedia or who knows. But then if you ask ChatGPT, who is Mary Lee Pfeiffer's son? It says, I don't know. I've never heard of that person, right? So somehow the knowledge is like maybe inside of it, but it's kind of sensitive to like the way in which you ask the question. And we can turn that problem around and we can say, well, if we ask the question the right way, we might get better answers. So there's this paper, Way It All 2022, that asks a math problem. So Johnny goes to the store and buys 5 apples and he drops 2 on the ground, but then half the apples go missing. And how many apples does Johnny have, And then it has an answer. And it actually, they found that if they just ask the question and then they put, for the answer, they already fill in, let's think step by step as a magic phrase, they get twice as many answers right, So, and nobody really knows why. That's the cool thing about these neural networks, right? So you can, maybe it's that by saying, let's think step by step, you're kind of forcing the model to think about the answer before giving the answer. And it's spending the same amount of compute on every time it generates a new word, so, or a new token. So maybe that's it, but that's actually doesn't account for all of it. And they tried a bunch of different phrases. They're like, let's think this through before giving the answer. And let's make sure that you know what you're talking about. I don't know. They tried a bunch of different things, and this one was by far the best. Let's think step by step. And so they gave it a name. They called it chain of thought prompting. And you see this everywhere in the machine learning word, chain of thought prompting. It just means adding that magic phrase. And probably what's happening, if you ask me, speculation time, is that somehow like those words often appear in tutorials. So kind of the data that it was trained on is kind of smarter data, So you're sort of accessing that part of the model where it was learning from like a textbook tutorial or something like that. And so it's imitating the behavior around there. That's why I think. One thing you can do is few shot prompting. So 0 shot means just ask the question and see what answer comes out. But few shot prompting, like 2 shot prompting, for example, is giving 2 examples of how a question would be answered and then asking the question. This works quite well. And so here's an example of the prompt that one of the prompts I can give to cosmosage, one that I recommend. That's first the system part. It says, you are an expert cosmology assistant. You're able to answer anything and blah, blah, blah. You are very smart. Because if you tell it to be smart, it'll be smarter. And then if you tell it to be dumb, then it'll be dumb. You really can just tell it be smart and it'll do better. And then I give a bunch of, just give 2 answers that I wrote myself that I think are high quality, or at least they're in the style that I like. And then the user types something in and pops up over here, and then the model fills in the response. So this is one way. This is my attempt at prompt engineering in cosmosage. So cosmosage version 4, version 0.4, I think it works pretty well. I'm pretty happy with it so far. It needs some work still, but it's not bad. So far, evaluation-wise, very little has been done. It's just me looking at the answers and being like, yeah, that's pretty good. But nobody else, as far as I know, has looked at the outputs, and maybe this is a time for people to judge whether these are good or not. But I'd love for somebody else to play with it, see if it's any good and any use to them. And then there are all these benchmarks and quantitative ways of evaluating a model, which I have also not yet used. Should I read one of these examples? Sure. Which one? That summary is pretty good. Let's do the summary here. So all I give it is summarize impact of beam far side lobe knowledge in the presence of foregrounds for LightWork. This is a paper that we recently published with the LightWork collaboration. And it generates new text. Yeah, this is not memorized from the abstract or anything like that. This is its understanding of that paper that it has memorized the semantic meaning of. So it says, this paper investigates the impact of beam far side lobes on the estimation of the tensor to scalar ratio in the presence of foregrounds for the LightWork mission. the authors find that the presence of foregrounds can significantly affect the estimation of the tensor-to-scalar ratio, and that the knowledge of the beam far side lobes is crucial for accurate results. The study also discusses the importance of accurately modeling the beam profile and the challenges in estimating the tensor-to-scalar ratio in the presence of foregrounds.
Pretty good. Pretty
It's
good.
not as
Yeah.
good as the abstract itself, but it's not bad, right?
Pretty good, yeah.
Yeah. I asked to hear what the best value of tau was, and this is correct, actually. It knows. Although it gives a citation of this weird B here. I guess this often happens in papers that there's a B added to it. I guess Plonk Collaboration put out multiple papers that year. I mean, I guess I know. And I asked it, what is the cross spectrum? Why is the cross spectrum not suffer from noise bias? And it sort of understands, like, oh, well, two, the noise processes are independent and therefore there's no correlation. And so on average, it understands like the ensemble average is that you have no effect of the noise in a cross spectrum. So that's pretty good. And then I asked it about a paper that I wrote many years ago that I put in the training set as well. And it nicely gives a detailed answer. I made this, of course, open source, you know, I mean, at the end of the day, I just want this to be useful to as many people as possible. So all of the code's on GitHub, it's just called cosmosage, and all of the models, all of the weights are on Hugging Face. So cosmosage version 0.1234, and hopefully soon 5. And what I'd really like an aspiration here is to provide this to anyone in the world who wants to use it, right? And so to have a little bit of an inference server where people can go and they can type in a question and it gives an answer. That does require a minimal amount of funding or something like that, where there's a kind of, because there does have to be a GPU that's running this all the time. So I haven't figured that part out yet, but that's the aspiration. Links are in here. I'll put these slides up on the wiki in case you want to check it out. Okay, caveat time. Never trust an LLM. Why would I say this? Well, the next word prediction optimizes for plausible text. That's all you're getting is plausible text. It's text that has the same statistical properties as the training set. And that does not optimize for factual accuracy or truthfulness. Here's some examples. What is the world record for crossing the English Channel entirely on foot? This, of course, makes no sense because, in case you didn't know, the English Channel is all water. So, cross it. And it just starts, ChatGPT just starts giving you a whole thing. It says, many people have attempted to cross the channel on foot, but it is very challenging and dangerous due to the strong currents and chilly water temperature. It starts a backtrack of it. It's typically done by a combination of swimming and walking, or only swimming. So it sort of realizes as it's going along that this doesn't make sense, but because of its auto-regressive nature, because it's fitting based on the tokens it's already put out, it's really hard for it to backpedal, it's really hard for it to be like, actually, that was wrong, and, it doesn't really know how to do that. Here's a citation that's completely made up. This doesn't point to anything. Here is some scary part, some racist part of the internet that it picked up and actually believes. Here is a question about a fictional work by Tolkien, but the answer, unfortunately, is more fictional than just fiction. It never actually happened in the book. And more links that don't work and stuff like that. So lots of examples of just lack of reliability. You can't never fully rely on a large language model's output. And this remains to be true. And I really want that to be very clear, and I'm working on this to be helpful, but I don't want anyone for any of these, GPT-4, any of them, taking the output as factual, because that's really just not what they're for. And so if you can't trust an LLM, then what are they actually good for? Why would I say that in a talk like this? And so let me just tell you what I use LLMs for, on a daily basis. So probably one of the primary things is verifiable information. It's stuff maybe I already know the answer, or maybe I can just check to make sure that the answer is correct. Explanations, I know A, I know B, how do you get logically between A and B? As a sounding board, just something to chat to. Often I don't even need the response, I'm just typing my question. I'm like, oh, wait, I'm not thinking about this the right way. It doesn't make sense, whatever. It's inspiration for brainstorming. Search terms. I love combining ChatGPT with Google. I'll give you an example. I was doing some chemistry thing for some weird reason. And I was like, what's the difference between something that's basic and something that's alkaline? And I'm like looking it up on Google, I'm like, basic versus alkaline, but it just doesn't get it, because basic means so many other, basic is a word that means something else. And I just couldn't get a good answer. So then I asked ChatGPT, what's the difference between basic and alkaline? And it gives me a bunch of crap that's not actually, it turns out later I find out it's not actually completely correct what it's saying, but it keeps using the terms basicity and alkalinity, So then I go back to Google and I search, what's the difference between basicity and alkalinity? And now I get all these chemistry websites that give me the correct answer. So it's the combination of a search tool where I can verify information and ChatGPT, where it can give me a bit of a thesaurus, a bit of extra language that gets me to the right answer. It's on the tip of my tongue, Programming. So I use GitHub Copilot every day. I really do. And it's when I'm typing and there's, I put some, how do I connect to the socket port, whatever, and then boom, comes out a big code chunk, and I just hit tab and it fills it in for me. It's basically autocomplete on steroids. And honestly speaking, I'm not exaggerating, my programming ability since I started using this is 10 times, like the speed, right? Not the quality I can get to, but the speed with which I write code has gone up by an order of magnitude. It really has. It's life-changing for me. And so, but again, don't rely on the output to be correct. Oftentimes it gives you stuff that doesn't even run or whatever. So two approaches for this. One is first pass programming. I get the LLM to give me a bunch of code, and then I just walk through line by line and just make sure that it makes sense. But if you are a very good programmer or computer scientist, you probably already write your unit tests before you write the code that's supposed to pass the tests. And in that case, if you've written the unit test, you can just get ChatGPT or cosmosage or some other LLM to write the code, and you can just see if it passes the unit test or not. Either you got to verify, either human verification or automatic verification. Writing, I think LLMs produce really nice text. The grammar is perfect. Certainly never a spelling mistake, and I quite like not always the style, but definitely the quality of the scientific writing. And when I'm writing a paper, I never copy and paste the output of ChatGPT, but I will, for example, I'll take a paragraph I just wrote, drop it into ChatGPT, and I say, give me 10 criticisms in bullet point form. And there it goes, doom, 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 doom. And then a lot of them don't make sense. And some of them are like, oh, wow, that's really helpful, actually. So I use it for scientific writing. And I think the reason it has perfect grammar is pretty subtle. And you can ask me in the questions if you want to hear my thoughts on that. So cosmosage is going to continue to improve. There are many ways to improve on the V4 that I showed you. Here are some important ones, starting with a stronger base model. So currently I have this 7 billion parameter model. I mean, there's some 34 billion parameter models out there that are much better. So I just start with a stronger base model. I should get it to perform better. The other is that I'm far from converged. I'm really compute limited. And so I could just keep training. And then the data set, I'm still using this 2-pass thing where I'm feeding it a bunch of like semi-junk, renderings of textbooks. If I could turn all of that into synthetic question answer pairs, I might get an even smarter cosmosage. And then extensions to the current effort include some ideas. I just put 4 of them here, but I have many more. One would be to do a Japanese version. That'd be cool. If somebody wants to work with me on that, I think that'd be fun. Feed it a bunch of Japanese data and see if it can become a cosmology assistant in Japanese. Or you might feed it just all of the languages, see if maybe we can get it to speak everything. The base model already speaks all the languages, so just need to Cosmo fine tune it. RAG, this is very popular, retrieval augmented generation. This is where the model can sort of, the model can sort of refer back to its knowledge base. It has sort of direct access to the knowledge base rather than just having been trained on it. This would be basically like tossing all the work I've done so far and starting with a different RAG solution, but it's an option. Then there are all these ideas out there that are really popular right now, like tree of thoughts and Q-star algorithm and beam search, which is very old actually. And all of those ideas refer to, let's just get the model to generate a couple different things, and we'll pick the best one, or maybe we'll get it to choose what the best one is, and then you can, from a given model, just get better outputs. So something like that would be cool to implement. And then this is cosmosage, but why don't we make hepsage or some, I mean, what do y'all work on, you know? Like you could, anything that, any field that you would like to train one of these on, I mean, all the code's public and we could totally do this for another field. And finally, really, like I mentioned before, an aspiration of mine is to provide this to anyone who wants to use it. Currently, you can download the weights. If you have some GPU, you can load it up and you can start generating text with it. But a clean web interface where we just have some server in this building or something that just serves people who want to ask it questions, I think would be very cool. So I'm open to collaborating with anyone who's interested. If you have some cool ideas for me, you know, just ask me a question now or talk to me after or some other time. If you have GPUs available, let me know. And if you're just interested in working on this with me, your time and effort, I'm sure could be put to good use. Here are a couple more slides here. So this is important, concerns about bias or AI safety or that sort of thing. In this case, bias. So I got Stable Diffusion running on my home computer. And I asked it to make an image of a team of successful scientists right after discovering a new phenomenon in the cosmic microwave background, celebration art, photorealistic. And of course, I get slightly balding white men only, right? 3 of them. And that's not good, you know? I mean, there are lots of, I mean, maybe there's some historical abundance of images like this, but we'd like maybe to depict a more diverse crowd there of celebrating CMB people. And so this problem is being studied by AI researchers quite extensively. Actually, I would say like maybe 8 out of 10 AI related or LLM papers that you read in the computer science part of the archive have some section about either its diversity issues or AI safety or something along those lines, concerns about bias. So one way is to, basically the best way, it's always garbage in, garbage out, you know, so the best way is to just have your training set, have lots of examples that you like, you know, and then if the output reflects the training set and you're happy with the training set, and it's all good. But for things like gender and ethnicity, you can make the model, you can build a layer on top of your LLM that's explicitly aware of this. It's like, okay, what am I generating? Okay, it's 3 people. And then actually there are models out there that do, then I will take a 10% chance that they are Pacific Islander and a 10% chance that they are African. And, you know, this kind of like, you can make it very explicit and make sure that you have a diverse people represented in your output. So that's another, I don't think that's a solution that's going to stay, you know, I think the solution really is to just have good training data. Let me leave you with 2 more slides here. And these are just my top 2 favorite computer science papers that I've read on the subject. Okay, so this paper is called Emergent Abilities of Large Language Models. I actually did a journal club on this paper in our CMB meeting that we have here some time ago. And what they find is lots of graphs that look like this. So they give some multiple choice tasks to the model, and then they have different models that are trained with different amounts of compute. And also, like, the more compute is more training data also. This is the smarter model, and that's the smaller, dumber model. And what they find is that the small models are not able to do the task. They just get 25%, which is random, out of a ABCD multiple choice question. And then at some size, the ability to do this task becomes better than random all of a sudden, meaning an ability emerges. And what these emerging abilities are things that were not in the training data. So these are new things that you're asking a large language model to do that it's never seen before. To me, that's the definition of intelligence. To me, the definition of intelligence, human or artificial, is taking what you already have learned and applying it to a new situation, to something you've never seen before. And so for me, really, I would say this is the essence of intelligence. So for example, one of the tasks is they do like 2 + 3 equals, and then the answer is 6, you know, and then they do 9 + 1 equals, and the answer is 11. And you give it a 5-shot prompt. So you give it 5 examples, and then you ask it for the 6th example. And if the model's smart, it realizes that you're not doing addition, you're doing addition +1, you know? And that's an ability that emerges just like this. When you get the model bigger, train it on more data, all of a sudden it starts being able to do that, right? And another example that's wild is this example. I'm sure you've been staring at it while I've had this slide up. If you really squint your eyes here, you might be able to see the word bench. here in ASCII art. So this is just a benchmark, but there are many examples like this. And you can ask the model like, hey, what does this say? And you just give it these characters, you just give it dot, asterisk, asterisk, dot, 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 and you give it in a linear series. You don't even tell it that it's multi-line like that. And then the model figures out like, oh, this is representing in the shapes of a B, and this is representing the shape of an E, and it's saying the word bench. And you can generate examples like this, and then I can ask the model. And this was one of these cases where their largest model was just barely, was getting to like 40% or something. So it was just emerging at the largest model size they could do. This is wild, right? This is something that they've never, this task was never in the intended training set, but suddenly it emerges out of this almost generalized intelligence that the model picks up.
So this is a discovery, and we don't know yet how it happens.
Yeah, that's right. We don't know how, and maybe more importantly, we don't know how long it'll scale for, right?
Right.
Yeah, maybe it'll get really good at tasks we haven't even thought of, And so the definition here they use is emergence is when quantitative changes in a system result in qualitative changes in behavior. So by increasing the amount of training compute, all of a sudden it's able to do something better than random where it wasn't before. And so yeah, what abilities will emerge next? And then really it's my favorite paper that I've read on the computer science part of the archive is this Sparks of AGI paper. This is this guy, Sebastian Bubeck. He had access to GPT-4 before it was released to the public. And he just wanted to show some of the cool things that GPT-4 can do, which is still today, 8 months later, the strongest model that we have. And he finds all kinds of classes of things that it can do. Those include some visual capabilities, even though the model was trained purely on language, logic and reasoning in ways that it hasn't seen in the training data, emulating emotional intelligence. There are these emotional benchmarks of how good of a therapist or something like that is the model. Creative storytelling, poetry. I really enjoy the poetry GPT-4 puts out. And code generation and understanding, like I said, this has made me a 10x programmer. I mean, I wasn't a very good programmer before, but I would say I'm decently fast now at least. So here's at the top here is an example of these visual capabilities. So this is you tell GPT-4, you're like, you have access to the following commands. This one's called draw a rectangle, and you have to give it a starting coordinate and an ending coordinate. This one's called draw a circle. And then you tell it, make a visual representation, given coordinates and sizes or whatever, shapes, draw me a cat, and GPT-4 comes up with this thing, which is, it could be better, but it wasn't trained to do this. It was just trained on language. Yeah, it was just trained on completing the next token. And the ability to draw these things has emerged. So somehow, I boil it down to this one sentence. The most efficient way to compress all of human knowledge or all of human writing is to understand the world that led to that writing. Yeah, so that it's a compression thing. It's like, because the model is only this big and you've fed it that much data, the best way to compress it is to rederive it all, right? It's to understand the world that generated that stuff in the first place. And that's how it picks up all these abilities out of nowhere, this kind of intelligence, really. So yeah, here's a picture of a dog, a truck, and an automobile. Here's another cool little one where they give it a kind of story. They say you start in the main hall, and there's one door to your left, and one door to your front, and one door to your right. Which one do you choose? And you're trying to make your way to the goal. And then the model answers, I would like to take the door on the left. And it says, you are in the kitchen. There are no other doors. There's only the door that you came from. Which door do you choose? And the model says, I want to go back. And in this way, in a little story, they get the model to run through this thing, and eventually it sort of randomly finds itself in the goal, right? And then they ask GPT-4, they say, draw me, using coordinates, draw me a map of the layout of the place that you've been to. Right, so from the model's perspective, it's seen a door, it's tried to go through it, it's gone back, it's done all this stuff, and then it's somehow able to it is able to reconstruct perfect. There's no mistakes here. This is a perfect map of the layout that it was put in. So yeah, I'll leave it here. This is a rapidly evolving field. Who knows where it's going to go next? And I think it would be actually a shame, to not take advantage of this technology. I'm certainly staying very much up to date with it, and I hope you all do as well. So thank you very much for your attention.
Yeah, thank you very much for the very interesting talk. Let's see if we get many questions. Chris?
So those 1,000 archive papers that you trained on, those were all cosmology.
Yeah.
So it's only really trained on.
Yeah, it's cosmology and a little bit of astroph.im, instrumentation for astrophysics.
So it might not, if I ask it a part of this question, maybe it's not.
It's certainly not the best at that. Yeah, we would
Okay.
like to, yeah.
So
might be better off
you
here.
have like plan to make it more general or not just cosmosage, but
Well, that was one of the ideas I put in, a high energy physics sage or something. And I mean, if you want to do it, you know, all the code's public and I can help you. So, yeah, why not?
I think it's already working on that. Other, some kind of, yeah, edge stage, like, I know that Atlas is working on the LLM as well, for Atlas.
But they're not planning to release it publicly, right? It's
Maybe
internal
not.
to Atlas.
I don't know,
It's trained on, well, it's trained on internal documents, so they don't want to release the model.
most probably.
I have a quick question at the end of at your last slide about, you know, you tell the story and ask them to.
See you.
Oh,
Sorry.
Draw.
I messed up.
It's fine. I just want to ask, so as in part of this process, how the memory came into, you know, the pictures, because I only familiar with ChatGPT in the sense that, you know, I ask the question, they give the answer. This seems to be like, you know, a real feedback between the user, right? And that, you know, tells the system that, hey, you choose the left, and, you know, I tell you what happened. So I just wondering how the, you know, the memory of this thing get updated as you
Okay,
actually do it.
yeah, so this is, okay, so there's three things that are important. One is the training data, the other is the prompt, the question you ask, and then there's the answers that the model gives. And the prompt and answers can be repeated. You can have a multi-turn conversation with ChatGPT, as you know. And that entire set of prompts is called the context window. And some models like Claude have 100,000 token context windows. So those could be really big, right? And so in this case, this entire game, if you're walking through these rooms, fits in the context window. So it's a repeated conversation with GPT-4, and it always has it in short-term working memory, if you like, in the context window. Does that answer your question?
Yeah, thank you.
Yeah, I enjoyed your talk very much, and then certainly, you know, I can now think about something like, for example, systems engineering sage, systemology sage, you know, to help people develop, you know, the project.
Yeah.
Yeah.
Going question about like, so you mentioned about LLM speaking, like, giving answer that's not true.
Mhm.
And think about like, is that a fundamental limit on those like, it's just, can people like, is there any limits that, we cannot improve on that, or like, I mean, like, if you can improve on the answer, be like 99% factual, then you can use it as a teaching tool, right? I mean, like, people can ask a question and then learn from the answer, ask a question, learn from the answer. That's like if we enlarge its usage, like, if the factuality of the answers can be ensured.
Yeah.
Right, so is there any fundamental limits on like those LLM model, like not able to ensure its accuracy?
Yeah, good question. So, I mean, the short answer is that we don't know, and I mean, the world doesn't know whether reliability will be a problem that will be solved, or whether it will remain. Fundamentally, what did I say? Next word prediction optimizes for plausible text, right? So it sounds about right, and that's what it's optimizing for, rather than some kind of factual accuracy or truthfulness. But maybe a truthfulness could be an emerging property. You know, maybe if the model gets big enough, or you can give it some examples, some negative examples when you're training, where you can give it an example where it produces a false output, and then you have an example where it says, "I don't know." And then you can give it, you have these techniques for it's called, the popular method these days called DPO, direct preference optimization. You give it a binary answer, you say which one's preferred. And that way you nudge the model into giving those kinds of answers. You can get it to say, I don't know when it doesn't know, but it's not fully, it's never 100% reliable. You know, every once in a while you still get junk from these models, and whether that will ever be solved in this paradigm, we don't know. There are other paradigms other than next word prediction that will give you factual answers, such as the RAG that I talked about, this retrieval augmented generation. You're using the language model more as a tool that has access to a knowledge base. And then it can go and be like, oh, actually, this is semantically similar to this one textbook I remember. And then it can go and look that up, and then it'll tell you this textbook says, and it'll quote from it, you know, and maybe. And so then that's guaranteed to be factual because it's directly giving you a quote.
Thanks.
Actually, I have one question. So when we read the research papers, one common thing that we do is we look at it and then we highlight the sentences that we think are important. So I'm thinking, is this a natural job for you know, a large language model to do? And if so, what's our so the first question is what amount of a training data is suitable for developing this type of application? And the second one is what do you see as the biggest challenge for this task?
So my first thought, naive thought when you say this, right, is like, oh, I will just annotate a bunch of papers and then I'll do supervised fine tuning to get the model to do that task too. This is not really going to work because it's going to take you your entire lifetime, you know, to highlight enough stuff. But what I, for example, do all the time is I ask that my large language model make the summary of, and then, you know, like a huge paper or something, and then it makes a pretty nice summary. So that would be like kind of collapsing it down to a lower cognitive load, or like only the important parts or something like that. I think your idea is cool to make it's like a model that's fine-tuned just to showing quotes that are really important or highlighting or something. I don't know. Have you heard of something like this? I haven't heard of that directly.
Not sure.
Yeah.
Yeah, do we have any other questions? I think we're past the hour, so let's thank our speaker once more.